É pronto, né? Ok, vamos. Good afternoon, everyone. Here is the optimization class at INPA. The name of the class is Computational Method of Optimization. Actually, it is the optimization tool, the second optimization class at INPA. The first one was by Professor Solodov in the previous semester, and it's about the convex analysis and some theoretical parts. And in this class, we will introduce mainly about algorithms for the unconstrained optimization and also constrained optimization. Okay, and in each class, we will give more or less a 30 minutes class, and you can see it on YouTube or you can see it personally at INPA. Okay, and it's a little bit different from the classical materials, in the textbooks, because usually in this kind of books about nonlinear programming or convex optimization, it is not very usual to talk about this topic, the monotone inclusion or the monotone operators. But actually, this is somehow can give you another perspective to understand a lot of problems in optimization or operational research, and it can unify a lot of different algorithms and methods in optimization. So both in the constrained optimization and unconstrained optimization, when we talk about like today the optimality condition, we will mention a little bit or talk about the monotone operator and some corresponding algorithms. Okay, this is a little bit from the classical courses class in the optimization. Okay, today we will first introduce some preliminaries from the convex analysis, and then we go to the optimality condition for unconstrained problems, and then we will introduce the maximal monotone inclusion problem and the proximal point method, and then I will give you several references to read about more. And actually, this proximal point method, which also didn't appear in many textbooks about optimization, it's somehow an abstract method, but it can give you a lot of things to help you understand the algorithms in optimization. Okay, so first preliminaries. The first is we want to see what is the set valued operator or set valued mapping. If T is from it's a set valued operator from Rn to Rn if it maps a point to a subset of Rn, okay? It may be empty, okay? And then we define the graph of this operator is a set in the higher dimension space, which is Rn times Rn, okay? It's a pair of x and u, which u is in the image of the T of x. Actually, sometimes we use graph T, or sometimes we use T itself to represent the graph of this operator. Okay, and next we will review about recall the convex function. Actually, in the following classes, we will introduce several algorithms, okay, for both unconstrained and unconstrained. Sometimes it may be convex, sometimes it may not be convex. But if the function is convex, then the convergence analysis will be elegant, and you will get a stronger convergence result than the general function, okay? So a function f from Rn to R is called convex if it satisfies the convex. The function value of the convex combination is less than the theta times fx plus 1 minus theta fy. For all theta belongs to 0 and 1, and for all x, y belongs to Rn. Actually, the domain of a function, of a convex function, it must be convex. Okay, of course, here we define the f is from the domain of f is a whole space. But if your domain is not the whole space, but it must be a convex set, or this convex combination doesn't make any sense if the domain is not convex. Okay, so if we study convex function, it will give you a lot of convenience. For example, in the convergence analysis. Okay, next we will recall the subdifferentiable of a convex function. Okay, actually, subdifferentiable of subdifferential. Sorry, it's a typo here. Subdifferential of a convex function is a set of the vector u which satisfies this inequality for any x belongs to Rn. Okay, of course, here we assume the domain of f is the whole space. What does it mean? For example, here we have a convex function. Okay, this function f is convex. We have a point x here. Okay, this is x. The subdifferential at point. Sorry, use z here. Okay, we use z here. The subdifferential of point z, it defines each element in this subdifferential defines a half space, okay, which can separate, which can contain the function f, okay. So the normal vector of this half space is the u, which belongs to the subdifferential of f at point z. Okay, so this is the definition of the subdifferential of a convex function. Actually, this set may be not singleton. For example, here, the function is smooth at point z. Okay, it's differentiable at point z. So in this case, if f is differentiable, we can see that the subdifferential of at point z, then the subdifferential of f at z is a singleton, which is just the gradient of f at point z. Okay, but if the function is not differentiable at this point, for example, we have the function like this. It's smooth on the left side, and at this point it's not differentiable. This point is z. So you see this supporting hyperplane or this half space is not unique. Okay, you can find a supporting hyperplane which defined by the subgradient like this, and also you can define another one. Okay, so you can have a u1 here, and you can have another normal vector related to this half space. Okay, this is u2. So in this case, if the function f is not differentiable at this point z, then its subdifferential is not a singleton anymore. It's not singleton anymore. Okay, this is what we will use in today's class. Okay, we need to be a little careful. Here, the function is single valued. Okay, but the subdifferential may not be single valued. Okay, sorry, it should be not single valued because it might be set valued mapping. Okay, next we will introduce a kind of operator or set valued mapping which is called monotone. Okay, we see mapping T from Rn to Rn is monotone if it satisfies this inequality. Okay, for any x, u, and y belongs to the graph, it satisfies this inequality. Actually, it's a kind of a generalization of the monotone function in the one dimension, okay? So if you assume that this mapping is a single valued, okay, you can use the f tx minus ty. The inner product with x minus y is greater than 0 for any x and y belongs to the domain or belongs to Rn, okay? And there is another definition here about the monotone operator is called maximum monotone, okay? What does it mean? If T is maximum monotone, you cannot find another monotone such that the graph of T will contains a graph of S properly, okay? Or we can say if T is monotone but not maximum, you can find another pair which not belongs to the T. Actually, it's graph of T, okay? Sometimes we use also T. You can find another pair U, X, and U which not belongs to the graph of T, but the T union with the pair X and U is still monotone, okay? Next, we will give you two examples which we say the first function, okay? The graph is here. We say this is monotone, but this is not maximum, okay? Because the graph of the small u can be contained properly in the graph of the capital U, okay? We say here this operator is maximum monotone. You say it's monotone because it doesn't decrease geometrically, and it's maximum because it can be not contained properly in another monotone operator. But we need to pay attention. This operator U is not single valued, okay? It's not single valued because at point x0 the image is a set, not a single point. Okay, this is the monotone operator. And okay, we have another graph to say, so this is not monotone, okay? This is monotone but not maximum, and this is maximum monotone and also single valued, okay? And we have a very important theorem about the relation between the subdifferential mappings of a convex function and the maximum monotonicity. Actually, the beginning of the study of this kind of monotone operators are not from operational research or optimization, but later people found this kind of operator, which monotone or maximum monotone, is connected with optimization and can give us a lot of interesting tools or ideas for designing the algorithms. So more and more people study these topics. One of the most important theory is that if we assume f is lower simultaneous proper convex function, okay, then the subdifferential of f is a maximum monotone operator. This also explains a little bit why we will study this topic, okay? We will not give proof of this theorem, but you can find the proof, of course, from the Rockefeller's book is from 1970, okay? It's this paper, and you can also use like Fitzpatrick functions. Actually, in the Rockefeller's book, you need to use some like dualities to prove it. But if you do not want to use duality, you can use like Fitzpatrick functions, and you can find the proof of this theorem by Fitzpatrick functions in this reference. Okay. So we go to the first topic of today, the optimality condition for unconstrained problems. Okay, a simple problems in optimization is we want to minimize the function f with not restriction, which means your feasible set is a whole space. Okay, you don't need to in each iteration, actually, in any cases, you do not need to consider whether your point is feasible or not feasible. Before we go to the specific algorithms, first we study the optimality condition. Here we mainly study about the necessary optimality condition, okay? We say if x star is an unconstrained local minimum of f from Rn to R, and we assume f is continuously differentiable in an open set S which containing x star, then we say the gradient of f at point x star equals 0, okay? In addition, if f is twice differentiable with twice continuously differentiable within S, then we can say the Hansen of f at x star is positive semi-definite, okay? The motivation of studying optimality condition is that, imagine you have an algorithm, okay? You make iterations step by step to you want to find the minimizer, okay? You want to minimize a function. But when will you stop? Okay, what is your stopping criteria? For example, you get a point which you think, okay, it's close enough to the solution. You think it's good, but what is the standard to stop the algorithm? One of the choice is you can check the necessary optimality condition, okay? Of course, if you want to solve this equation, okay, this maybe non-linear equation, it would be difficult. But if you check whether at some point xk, whether this the norm of the gradient is small enough, it's much easier than solving this system, okay? This is one of the motivations. On the other hand, even if it is very difficult sometimes to solve this nonlinear equation, but we can go a little bit deeper in this direction later. Okay, next we prove it. First, we prove the first order equation. Okay, the first order necessary condition, which is the gradient equals 0. First, we give some fixed vector d. Okay, and we're using the chain rule for this differentiable function related to the scalar alpha. And it's differentiable because we assume f is differentiable, okay, in an open set containing x star. And we have this inequality, okay, and this inequality holds first because we know x star is a local minimizer, okay, local minimizer, and so this is greater than 0, and then we take alpha approaches 0, okay, then we have the d transpose the gradient of x star is greater than 0, okay. Since here this operator d is arbitrary, okay, we can get the same inequality holds for not for d but for the minus d, okay, so we can get this d transpose the gradient of fx star is also smaller than or equal to 0. So we can get, sorry, there is a typo here. This should be d transpose the gradient of x star equals 0 for any d belongs to Rn. Okay, so since this equality holds for arbitrary d belongs to Rn, so it means the gradient of x star equals 0. Okay, so this is the first order necessary condition for the unconstrained optimization problem. Then we prove the second order necessary condition, which is the Hansen is positive semi-definite. Okay, so the assumption is that f is twice continuously differentiable. We give d is any vector in Rn. Okay, for any positive for any alpha, we use the second order expansion like this, okay? This is second order expansion. And since we already proved the first order condition, if x star is a minimum, local minimum, okay? So we have the gradient of f equals to of x star equals 0 because of the local optimality of x star, okay? we can say for sufficient small epsilon alpha or epsilon greater than 0, for any alpha belongs to 0 and the epsilon, we have this inequality, okay? We have this inequality because of the optimality of the x star, so it's greater than 0, and since this alpha is not equal 0, we can divide it both sides by alpha square. So we can have this term, this 1 over 2 d transpose the gradient square f x star d plus this O alpha square over alpha square is greater than 0. Then we take the limit alpha approaches 0 and using that this term approaches 0 when alpha approaches 0, okay? So we can get this term is greater than 0 for any d in Rn, okay? For any d, any vector in Rn. So this means the Hansen of f at point x star is positive definite, okay? So this is what we proved. What we proved about the necessary optimality condition. First, if first order is the gradient equals 0, and the second order is the Hansen is positive semi-definite. Okay, so if the function is convex, the case becomes more interesting. Okay, if we assume f is differentiable and convex, then this condition is not only necessary, but it's also sufficient. So it becomes a sufficient and necessary condition for the unconstrained optimization problems. Okay, if f is only convex, then the condition is that the 0 belongs to the subgradient of f at the point x star. Okay. Next, we will discuss more about this. The case 0 belongs to the subgradient of f at point x star. As we mentioned in the preliminary, if f is convex, okay, we do not assume it's differentiable anymore in this case. The operator of the mapping, the subdifferential is convex is a maximum monotone operator, okay? So now these problems becomes a special case of the maximum monotone equilibrium problems, which means we want to find a point x such that 0 belongs to tx, where t is a maximum monotone operator. Okay, so we can see that the optimality condition of unconstrained optimization problems of a convex function, okay, it's a special case of the maximum monotone equilibrium problems, which means we want to find x such that 0 belongs to tx. Okay, so actually there are some algorithms to solve this kind of maximum monotone equilibrium problems. One of them is the proximal point method, okay? And what is a proximal point method? Okay, we begin from here. First, if 0 belongs to tx, it is equivalent to 0 belongs to lambda tx, okay? It's equivalent to x belongs to x plus lambda tx. And it's equivalent to x belongs to the identity plus I tx. And it's also equivalent to the identity plus lambda t minus x equals x. Actually, we can say from this equilibrium problem, 0 belongs to x, is equivalent to this one, this fixed point. Okay, this somehow, if you regarded this I plus lambda t as an operator, this x is the fixed point of this operator, okay? Or it's x equals to x is a fixed point of this inverse of the inverse of this operator, okay? So generally speaking, we can conclude that x belongs to t is equivalent to x belongs to the fixed point of this operator with a color red. Okay. Maybe you have a doubt that why didn't we use the fixed point about this operator, or instead of using this red one, because it looks like this red operator with inverse may be more complicated because you have the inverse here. Yeah, we may think it's more complicated to compute. The reason why is if the operator t is maximum monotone, the inverse operator which named the resultant of operator t has better properties, which is more convenient to design for designing algorithms. Okay. We define the resultant of a maximum monotone operator is defined the g lambda t, okay, which equals to the inverse of the identity plus lambda t. What we can conclude about this resultant or inverse operator? First, it's single valued. Okay, since it's a single valued, if you use this operator to define a fixed point iteration like this, okay, if we use this operator to define algorithms, which is called proximal point operator or proximal point method. Since if the operator is single valued, you will not be confused how to find the next point, or the next point is well defined. Okay, and it's a surjective, so it also means it's well defined. You have no problems with the domains. Okay, and another very important property about this operator, resultant of the maximum monotone operator, is it's non-expensive, or furthermore, you can say it's formally non-expensive. And the third property here gives or guarantee the convergence of the proximal point method. Of course, we will not explain more wide convergence and what is the non-expensive, but you can find the more detailed discussions in the reference which I mentioned, what I will mention later. Okay. Okay, but here we discussed a little bit between the proximal point and the gradient descent, which we will discuss next class. Okay, if we want, we go back a little bit. Okay, now we have algorithms. Okay, this proximal point method, which uses the resultant, which is the inverse of the identity plus of this maximum monotone operator. But why did we study the maximum monotone inclusion problems? Let's go back. Because the sufficient and necessary condition for minimizing a convex function, which is 0 belongs to the subgradient subdifferential of x star, is a special case of these problems. Okay, so we want to use the algorithms we define here to solve the problems or to solve the optimality condition of minimizing a convex function. So what can we do? Okay, so what is the proximal point method? Xk plus 1 equals to the resultant of xk, which is equivalent to this. This is just by definition. Okay, here we use equality because this is single valued, okay, which I mentioned before. So that's why we can use equality here, but we can only use inclusion here, okay, because this operator may not be single valued, okay, may be a set valued mapping. And then we have an equivalent statement like this, and then we have a eventually equivalent like this. So here we take or we use t equals to the gradient of f or subgradient of f, okay. Anyway, so we have this iteration, okay, this iteration or this scheme. Actually, here this becomes equality because we use a gradient, okay? Because the gradient is the single-valued mapping, okay? If it is differentiable. But if you are familiar with the gradient method, you will discuss this is not the same with the gradient method which we are familiar with, okay? Because if it is gradient method, this here should be xk. Or in another way, how can you get the gradient of f at the next point before you go to the next point? So it's not a very good method, okay? And you can also interpret it with the backward Euler method or the forward Euler method, okay? So this somehow we can call it implicit gradient method, or the classical one we can call it explicit gradient method, okay? So in the general gradient method, we use gradient of f at point xk. But in this explicit or the proximal point method, we use gradient from the next step. Actually, we can discuss a little bit more about these algorithms. Okay, so xk plus 1 equals to xk minus alpha, the gradient of f xk plus 1. Okay, this is from the xk plus 1 equals to the resolvent of operator t, x, the identity plus lambda t inverse. Oh, no, sorry. xk, and the t is the gradient of f. Okay. Okay, if we rewrite this iteration, okay, like this, xk plus 1 minus xk plus lambda, the gradient of f, xk plus 1 equals 0. Okay, so we know if xk is the solution of this system, we can get xk plus 1 belongs to the argmin of x. Okay, we can find the original function of this part is 1 over 2 x minus xk square, and this part is of course we can divide it by here we divide it by lambda. Okay, so we have 1 over lambda here. Okay, so here it's 1 over 2 lambda and plus f of x. Okay, so this is what we get from the proximal point method. Okay, this is the proximal point method. Okay, we take the operator is a gradient, so we get this, but we see this is not practical because you cannot know the gradient in the next step, okay, in the xk plus 1, because this point is what we want to know. So we rewrite it, okay, and since x equals to this, so this equation might be the optimality condition of some optimization problems, okay. So this equation is the optimality condition of these problems, okay. Of course, if we can change the order of this, then we get xk plus 1 belongs to, I will write it, xk plus 1 belongs to the argmin of x fx plus 1 over 2 lambda x minus xk squared. Okay, finally we get this. If you want to use proximal point method to minimizing a convex function, okay, then it is iteration like this. But this is not practical. So we read it and we regarded this equation as an optimality condition for minimizing this function. So we get next point is argmin, which is the solution of these problems. Okay, but to minimize this function sometimes is the same difficult as minimize the original function. Okay, this subproblem, we call it the subproblem in the proximal point method. This sometimes is the same difficult as minimize f. Okay. The good thing is we have a regularization terms here. So sometimes it makes the subproblems becomes not ill conditioned. Okay, it becomes better than the original problems. But minimize this problem sometimes is still very difficult. So that's why if the function, of course, if you have a structure of the original problems, okay, if you have an explicit form solution, closed form of these subproblems, it's okay. But if you do not have closed form of these subproblems, then generally speaking, it's still a hard problem. But if we use the subgradient of xk instead of xk plus 1, then we get the gradient descent method, okay? Of course, with lambda. And this is much more practice than this one, okay? Or than the one I mentioned here in the blackboard. So this is what we call the gradient descent method, and this is what we will discuss in the next class, okay? So we give 3 references. First is a book about the large-scale convex optimization algorithm and analysis via monotone operators. This book you can download from the website. They also have the corresponding video course on YouTube. And you can find the materials about what I said about the maximum monotone operators and the proximal point method. Of course, you can also find it in a mini course impact, which I gave it in the last semester, in the last summer school. Okay, this is a link, and also you can find many interesting material in the optimization course. Of course, here is called Convex Optimization 2 in the website of the Stanford University. The materials there are not very complicated, are very friendly for the audience, even if you are not from optimization area. And about the textbooks, of course you can use the textbook from INPA, which is in Portuguese version, which is good book. And you can also use like Bataseca's nonlinear programming or the Stem-Boyd convex optimization. But for this course, we do not have a fixed context book. In each classes, I will give the specific reference. Okay, so this is all the material, all the topics I talk about today. Next class will be on Friday. We will discuss about the gradient descent method. Okay, thank you all. Double.